We turn to discuss impulse noise removal, which is nothing but a direct extension of the in-painting we just described. Observe that throughout the discussion on in-painting, we use the underlying assumption that the location of the missing pixels is known to us. That is, we know where the holes in the image are. What if we refer to this information as missing as well? In such a case, we are getting a corrupted image, and we need to discover by ourselves which pixels are problematic and then replace them. The impulse noise problem is of such nature. Let's define it clearly. We are given the corrupted image in which p% of its content in random locations are wrong. We should assume that their gray values are severely distorted by randomly adding or subtracting to them a large value, say 50. As a consequence, these corrupted pixels appear either darker or brighter compared to their neighborhood. This explains why we often refer to this as salt and pepper noise. Here is an example to illustrate this noise behavior. In this case, 10% of the pixels are corrupted this way. Now, what have we been taught to do in such situations? The answer is median filter. Basically, we replace each pixel by the median value of its local neighborhood, and this is known to be quite effective for salt and pepper noise removal. Now, let's offer our alternative, which will be based on SparseLand. We borrow the median filter, using it as a detector for the corrupted pixels. If a pixel is much deviated from the median of its neighborhood, we define it as missing. And then, given the mask, we simply consider our problem as an in-painting one, where those masked pixels are to be resurrected while keeping the rest of the pixels intact. In fact, we shall do something similar with the median filter. We will modify the pixels only where the mask points to. And here are the results. The top left image is the given one. The mask on top of it is shown as dark pixels. The regular median filter gives an average error of 7.42. And when we selectively employ the median to the mask pixels, this error drops to 6.52. The SparseLand proposed scheme that in-paints the mask pixels using fixed DCT dictionary gives the lowest error of 5.82. This is just an initial idea, and it can be further improved in various ways. For example, we could train the dictionary in this process, proceed with several rounds of iterations, and recompute the mask, and so on.